theta 1, A3. If we put in the numbers, go back to the loss table. Go back to the loss table. This loss was 0, this loss was 1, and this loss was 3. And so if you just do the arithmetic, the expected loss using strategy S6, if in fact it's a sunny day, is 0.70. Okay, this is the critical thought in evaluating how good the strategy is. And now we do the same thing. What if the state of nature is theta 2, rainy? And we do exactly the same thing. The expected loss will be the loss if it's theta 2 and we take action A1, and the weather forecaster calls that 20% of the time. 30% of the time, 50% of the time. Put in the numbers from that loss table, and it turns out to be 2.90. Okay, let's stop for a minute. What this has done is it's quantified for us how good is S6. And it gives us two numbers to answer that. It says S6 is this good if in fact it's a sunny day. And S6 is this good if in fact it's a rainy day. Ideally, what would you like? Ideally, what would you like for a strategy? You'd like it to be 0 and 0. You'd like to lose nothing if it's sunny. You'd like to lose nothing if it's rainy. Now that never happens in reality. Never. Because there's always uncertainty. Here you have the uncertainty showing up, and we put it in as the weather forecaster. Okay. Now, an easy way to keep track of this, those of you that are thinking, how would I do this in general? It's just doing it in this fashion. It's putting the state of natures here. We have 2. Putting the loss table here. Remember, we had that back a few slides. And then putting the action probability. This is the weather forecaster. And you get the 2.05 by taking 0 times this, 1 times this, 3 times this gives you the 2.05. And 5 times 0.5, 3 times this, 2 times this. So these are the expected losses if you take the S22 strategy, which was the opposite of S6. Okay? So at least from this little illustration, it's pretty clear that S22 is worse than the S6 strategy. If it's sunny, the loss here is 2.06. I think on the previous slide it was 0.7. And the loss here is 3.8. I think on the previous slide it was 2.9. So this one, no matter if it's sunny or rainy, has a higher expected loss than S6. So those of you that said strategy S6 would have been your choice, you're certainly better than those folks that said S22. It makes no difference if it's sunny or rainy. All right. Now, you could go ahead and calculate these for all 27 strategies, right? Just do the same thing. It's a big algebra problem, but you could do it. And you'd have a table that looks like this. It gives the expected loss if it's sunny, the expected loss if it's rainy, and so on. Now what do? You've got this table now, the 27 strategies, and you've got the expected losses if it's sunny and rainy. All right. you can plot the strategies on a two-dimensional plot, the expected losses for each of the two states of nature forming the axes. You all have done plots of data before. Exactly what we'll do here. And then the geometry will reveal the solution to us. All right, so there's a plot for strategy 1. The expected loss when it's sunny is 0. The expected loss when it was rainy was 5. So this point right here is, if you will, the risk profile of strategy 1. And I've done that for all 27 strategies. We all don't look impressed with this. But it's very revealing in the following sense. Let's just look at strategy 15 here. See where it's plotted? Would you ever use this strategy versus 15? Why? Why not?
More loss. Higher risk.
It makes no difference if it's risk when sun or risk with rain. This value is always higher than the one for 15. So no matter what, you would never use, what's going on here? You would never use this strategy versus any strategy down here. Is this all right? Pretty clear? So it's a way to sort through these 27 strategies and throw some away because you would never use them. There's always a strategy such as this one that does better on the sunny days and better on the rainy days. So which strategies should you look at? Well, just envision putting a little, let's look at this one for 2. Look at a line here and a line here. Look at the lower left-hand quadrant from the point. If there's nothing in there, that's a strategy that you would consider. If there were a strategy in there like this point, if I go down and over, there's points down here in that lower left-hand quadrant. If there are points in the lower left-hand quadrant, you would not use that strategy because you can find one or more that has a lower risk on either of the two outcomes. So, this is great. This is what has mathematics done for us. It's given us a way to look at all 27 strategies and throw a bunch of them out. Because we know there's other strategies that, in our phraseology, dominate as a lower risk for sun, a lower risk for rain. This okay? All right. So SI is dominated by a strategy SK if SK is in the lower left quadrant of SI. That's what we just sort of sketched out on the geometry in the previous slide. And we call an admissible strategy a strategy where no strategy is in the lower left quadrant of that strategy's risk point. An admissible strategy is one, such as 6, that has no other strategies in the lower left-hand quadrant. 27, it's an admissible strategy. There's no strategies down here that would be uniformly better than that. All right, so let's quickly recap where we are. We've got our problem. We talked about states of nature. We talked about the consequences, the losses. We talked about uncertainty. We quantified it here as a weather forecaster. We looked at all the strategies. There's a lot of them, 27 here. But we found a way to sort through them. And the only ones that we have to concern ourselves with are these admissible ones. There's still several of them, but it's a lot better than 27. Okay. All I've done here is I've connected by a line the admissible strategy. So you can see this. This one connects the admissible strategies. Okay, here's the admissible strategies. Now we're down to 3, 6, there's only 8 admissible strategies. If you answered my homework problem and chose any other strategy but these, however many, what did I say, 8? 8. If you chose any other strategy but these 8, then you're wrong. You're wrong in the sense that one of these 8 will be uniformly better than whatever it was that you chose. Okay? Now, how do we decide among these 8 which ones to go with? Well, that depends on how many sunny days there are and how many rainy days there are. If every day was rainy, then you would choose this strategy because the risk when it's a rainy day is 2, and that's lower than any of the other ones. So if every day was rainy, I would go with S27. What if every day is sunny? I live in, I don't know, Florida or someplace. Every day is sunny. Strategy F1 has a loss of 0. So that would be better. So which of these strategies is best depends on what's the frequency of sunny days and the frequency of rainy days.
6.
Okay, so the probability of sunny and the probability of rainy, that's critical. Let's suppose that half the days are sunny and half the days are rainy. What's the risk of S1? Well, on half the days, you're going to lose 0, and on half the days, you're going to lose 5. So your overall risk would be 0 times 0.5, half the days that are sunny, and 5 times 0.5, half the days are rainy. So using that strategy, your overall risk would be 2.5. Is this all right? And so you got the idea on how you do it for the other strategies. Notice now, there is no right or wrong answer. You and you could choose different strategies because you believe half the days are rainy and half are sunny, but you believe 90% are rainy and 10% are sunny. And so when you do your arithmetic, you may come out with 2 different strategies. That's okay. Your choices would be correct given your assumptions on the probabilities of the states of nature. Okay? All right. Geometry. Most of you have had geometry. Let's just go back a minute. Notice the overall risk is a weighted average. The risk for sunny times the probability of sunny. The risk of rain times the probability of rain. This is an equation of a straight line. And so that thing defines straight lines with slope minus the probability of sun divided by the probability of rain. And the risk, R, increases as that line goes up in this fashion. In a parallel fashion. And so just using geometry, I can solve this problem right now by putting a ruler down on my little graph and moving it up parallel until I bump into these admissible strategies. And whichever one I bump into first is the best selection.